uh, the nature of this electronic transition from, if you consider the N2 pi star, then N2 pi star. So if molecule is a non-bonding molecule in that case, so it is N, and that excited to pi star also. If it is non-bonding orbital is there, that also excited to the sigma star as like this. So this is a ground state for the non-bonding N, and excited is if for pi, and it is also for sigma, depend on what type of the transition is takes place in specific non-bonding orbital. If consider pi, it is a specifically double bond containing compound, it is a bonding orbital, and that is excited to the pi to pi star. Pi to pi star. So this is pi to star. Again it also for pi to pi star or pi to specifically pi star, depending upon what type of the interaction is. There is also the pi sigma to sigma star or sigma to pi star also. So depending upon what type of the compound in a ground states or specific bonding and non-bonding and conjugation system, that is get excited to the anti-bonding orbital, and it is denoted by the pi orbital. Then next is the specifically interaction in case of the nature of electromagnetic transition in pi to pi star. If you consider for a molecule that possesses the pi bond like alkene, alkyne, aromatic, acryl compound or nitrile. So what these are the double bond containing compounds. So pi, it is the first state, and it is a bonding state, and it is get anti-bonding towards the excited state of pi star. So light can promote an electron from pi bonding molecular orbital to a anti-bonding pi star anti-bonding orbital in this case. So this is called as pi to pi star transition, and it is actually strong, and it is high excitation coefficient E. So group of the atom involved in a pi bonding are thus often as called as the chromophore. So whatever the chromophores are there, they are having the pi electronics transition in it. So pi electrons. So the transition energy can be indicated or indication of the different types of the pi bond. And so this, for example, carbon-carbon, carbon-oxygen, or the carbon-nitrogen in a nitrile group. Then if you consider the N to pi star, N means non-bonding and pi star means the anti-bonding. So N to pi star, so transition. So lone pair electron that exists in oxygen, lone pair electron that exists on oxygen, that will also, some of the compound nitrogen atom maybe promote their non-bonding molecular orbital to a pi anti-bonding molecular orbital, that is pi star. So the N, it is indicated for the lone pair of electron containing compound, and that excited to the anti-bonding orbital pi orbital. So this is called as a N to pi star transition and required less energy, that is longer wavelength. Less energy means longer wavelength. High energy means shorter wavelength. So compared with that pi to pi star transition within the same chromophore. So however, the transition probably, it is usually much lower. Transition probability is much lower in this case, that is N to pi star transition. Then next is the N to sigma star transition. N for the non-bonding and sigma star is a single bond anti-bonding transition. So saturated compound with a substituents containing lone pair of electron. Lone pair is for the non-bonding N, as a water, ammonia, hydrogen disulfide, only have a N to sigma star and sigma to sigma star transition in the UV visible radiation. So we will come to know depending upon what type of the particular compound containing antibond containing the non-bonding lone pair of electron, or a single single bond containing compound, depending upon they comes to as a ground state, is a self ground state, and that gives the excited state in an anti-bonding orbital. So if you consider the basic is n as a non bonding electron, that will converted in, or that will come into the non-bonding orbital of pi star or sigma star, as like this. Then in case of the sigma sigma transition, when it is sigma sigma transition takes place, when the transition metal ion solution are colored as a result of their particularly field sigma level, which allow the promotion of electron to excited to the absorption relatively low energy visible light. So it is a color matter compound, in this case metal compound. So the bonds are often broad and strongly influenced by the chemical environment, and they are also vary in this case. Then the charge transfer transition. So some of cases the charge transfer is expressed in a transition. So much stronger absorption is found in a complex metals ions with some suitable organic chelating agents. So chelating agents are responsible for the strong absorption radiation and produces a charge transfer complex. So electron may be transferred from a metal to ligand, or a vice versa, as like this, because it forms the chelates. So this high transition probability is exploit to a quantitative detection ions in a solution in this case. So there are the number of chelating agent available which may or may not complex selectively, where there is a more than one type of the metal ion present. For example, 110 phenanthroline is a common chelate for the analysis of the ferrous. Then theory of the spectrophotometry. So theory of the spectrophotometry, particularly UV and visible, it is the same. Then when a light is incident on a homogeneous medium, a part of incident light is reflected. Part of light is reflected here, and a part is absorbed by the matter object, and the remainder is transmitted as such. So what will be happening is, consider our light source is there. If it is UV, if it is specifically IR, it absorbed by the object. Some of the get reflected and some of get transmitted in this way. So this is of the consideration of the specifically absorption, transmission, reflection of the light in this spectroscopy or phenomena. So what will happen? We consider all those things in equation form. So I0 is equal to IA, I plus IT plus IR. So what is I0, IA, IT, IR? So where I0 is incident light, I is absorbed light, and IR is reflected light, and IT is a transmitted light. So 0 indicate the incident light, then A is indicated absorbed, and R is reflected, and T is transmitted. So if comparison cell is used, value IR, that is the reflection, is very small. It is 4% can be emitted, means reflection is 4%. For example, it becomes reflection is negligible consideration. So equation becomes very short in this case. So I0 is equal to IA plus IT only. We don't want to consider the IR reflection in this case. So Brogger, one of the scientists, actually investigate the range of the absorption light with the thickness of the medium. So but Lamberts, who simply extend the compact development by the Berger. So after his study of thickness, particular Lamberts study further for this phenomena. So however, two separate laws govern the absorption, are generally known as Lambert's and Beer's. So we want to know about what is meant by Lambert's law. In that, when a beam of light is allowed to pass through the transparent medium, beam of light allowed to pass into transparent medium, the rate of decrease of intensity with the thickness, he considered the thickness of medium is directly proportional to the intensity of the light. So Beer's law state that when a beam of light is allowed to pass through the transparent medium, the rate of the decrease in intensity, means decrease in intensity of thickness of medium, is directly proportional to the intensity of the light. So mathematically he create an equation in the form of derivation of this. So minus di upon dt, this derivation for the incident light and with the thickness is directly proportional to the I. So where is first equation becomes I minus I di upon dt is equal to the I ki. It is the first equation form. So where I is equal to intensity of the incident light wavelength and T is thickness of the medium and K is a proportionality factor or constant. So we want to integrate this equation. So integrating the equation first and put I0 is equal to I0. So where T is equal to 0 in this case. So integration I0 upon IT is equal to KT, and where the equation becomes IT is equal to I0 e raised to minus KT. So it is a solved equation. So I0 is equal to intensity of the incident light wavelength, I is equal to the intensity of the transmitted light, and K is equal to constant depend upon the wavelength and absorbing medium. So changing the equation second, this equation we want to change for the natural logarithm. So we take the logarithm of this equation. So IT is equal to I0 logarithm taking log from both sides, it becomes I10 is equal to I0 10 is equal to minus raised to 0.434 KT is equal to I0 10 raised to minus KT is the third equation, where K is equal to small k upon 2.3036. It becomes, so it is a solved equation for the logarithm, taking logarithm in both sides. So K is equal to the absorption coefficient, in this case capital K. Then it is a reciprocal the thickness which is required to reduce the length to 1 by 10 of its intensity. So above definition follows the equation 3. So it becomes KT upon K0 equals to 0.1 is equal to 10 raised to minus KT. KT is equal to becomes 1 by solving K is proportional to 1 by T. So the ratio of I0 upon IT is equal to transmittance, and taking its log, it becomes absorbance. So it is solved equation, and ultimately it will get the transmittance and absorbance, that is ratio IR upon IT and log IT upon I0 respectively for transmission and absorption, T and for A. So absorbance was termed as a density N or the extension coefficient E. So ratio I0 upon IT is extreme opacity is equal A is equal to log I0 upon AT, so absorbance. So then we want to know about what is Beer's law. So it is a Lambert's law shows the logarithmic relation between the transmitted and the length of the optical path through the sample. So the Beer's observed that similar relation hold between the transmittance and the concentration of the solution, and that is the intensity of a beam of monochromatic light decreases exponentially in a concentration of the absorbing substance. So intensity of beam of light and monochromatic light decreases exponentially with the increase in concentration. It related to concentration, not a thickness. It is opposite to of the Lambert's law. So equation 2 becomes IT is equal to I0 E upon K dash minus K dash T. I0 is equal to I0 10, I is equal to I0 raised to 10 minus 0.434 K dash C. IT is equal to I0 10 raised to minus K dash C. So it is solved, become 4 equations. So where K small k dash and K dash capital K dash are constant and C is concentration of the absorbing substance. So on combining both of 3 and 4 equation, it becomes IT is equal to I0 upon I0 10 raised to ACT and logarithm I0 upon IT is equal to ACT 6 equation.